Perpendicular lines. Our objective is to prove and apply theorems about perpendicular lines. Well, why learn this? Rip currents are strong currents that flow away from the shore and are perpendicular to it. A swimmer who gets caught in a rip current can get swept far out to sea. Let's look at a couple of vocabulary terms. A perpendicular bisector. A perpendicular bisector is a line perpendicular to a segment at the segment's midpoint. The distance from a point to a line is the length of that perpendicular segment from the point to the line. Think of it this way. The shortest distance to get from any one point to another is a direct path. Well, the most direct path is to meet it perpendicularly. Let's look at an example. Name the shortest segment from point P to line AC. Well, the shortest distance is going to be from point P, and it's going to meet AC perpendicularly. Well, that would be PB. So PB is our shortest distance. When you're trying to write an inequality, use the fact that, well, if PB is your shortest distance, all your other distances must be greater than that. So in this case, PA is going to be greater than PB. Now you can sort of just substitute your values in. So PA had the value x plus 3, and then PB had the value of 5. Then we can solve for x by subtracting 3 on both sides, and we get the fact that x must be greater than 2. Let's look at a few theorems. If two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So if you have a line and you cut it in half, so that way you have two angles that are the same, they're both going to have to be 90 degrees because one line makes 180, half of 180 is 90. Alright, let's get a little more specific here. We have the perpendicular transversal theorem. In a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. Think of it this way. If both of these lines, N and P, are parallel to each other, then if you're looking at the angle on the top right here, if that's 90, the corresponding angle to this angle here would be on the top here, which would also have to be 90, which forces line Q to be perpendicular to line P. This one's almost backwards. There's a slight variation to it. If two coplanar lines are perpendicular to the same line, then the two lines are parallel to each other. Let's look at the proof for the perpendicular transversal theorem. For the purpose of this video, we will use a two-column proof. So we need our statements and, of course, our reasons. Can't have statements without those reasons. Alright, so in this proof, we're given the fact that line BC is parallel to line DE and that AB is perpendicular to line BC. So let's start with our first given. So we have BC is parallel to DE, and they are both lines. And we are allowed to state that because they gave it to us. How nice of them. Alright, so let's go with our next step. Well, if they gave us the fact that these two lines are parallel, we had mentioned about corresponding angles when we were looking at the theorem itself. So what two angles might we want to state are congruent in some way, shape, or form here? Well, that would be angle ABC. So this angle here needs to be congruent to angle BDE. And we know that they're both congruent because of the corresponding angles postulate. Alright, let's go to our next step here. Alright, well, we're also given that line AB is in fact nice and perpendicular to line BC. And they were nice enough to give that as well. So that was given to us. Alright, well, using the idea that we've got corresponding angles and then we've got things that are perpendicular, we might want to get an angle measure in there so that we have a value we can play with. So, if line AB is perpendicular to BC, we know that angle ABC must in fact be equal to 90 degrees. And we use the definition of the definition of perpendicular. Getting ahead of myself. So, because they're perpendicular to each other, we know that that angle has to be 90. Okay, let's keep going. Well, if angle ABC equals 90, we have an equal sign here, and we have a congruent sign here. So to be able to manipulate some things, we kind of have to have them both being the same symbol. So, therefore, we can take this congruence piece here and change it into an equal by saying that the measure of angle ABC must in fact be equal to the measure of angle of BDE, and that would be the definition of congruent angles. As if they are congruent, then their measures are in fact equal to each other. Okay, so now that we're both equal, we can now utilize measurement values and substitute things in. So, we can substitute 90 in for the measure of angle ABC. So now we have 90 equals the measure of angle BDE. And to do that, we just kind of use some substitution. It does also follow the pattern for transitive property of equality. I'll accept either substitution or transitive property for this one, because depending on the way you thought about it, you might have gone with substitution. And the seventh step here, our last step, well, if the measure of angle BDE is 90 degrees, then we just can kind of go a little bit backwards and go, oh, well, if it's perpendicular, it means it's 90. Well, if it's 90, it means it's perpendicular. So we have AB is in fact perpendicular to DE, and we can use the fact that the definition of perpendicular angles give us that, or perpendicular lines give us that, rather. Alright, well, let's look at another proof. We're going to write a two-column proof of this one. We have that we're given angle EHF is congruent to angle HFG. So these two angles are congruent. And we are also given that line FG is in fact perpendicular to line GH. And we would like to prove that EH, highlight that, our goal is to prove that EH is in fact perpendicular to GH as well. Okay, so let's start with our given. So we're starting with the fact that angle EHF is in fact congruent to angle HFG, and we know that because they were nice enough to give that to us. So given. And then we have the fact that EH is going to be parallel to FG, because if you notice, these two angles here form alternate interior angles. So if alternate interior angles are congruent, then the lines must be parallel, and the theorem that states that would be the converse of the alternate interior angles theorem. Alright, and our next step here, well, if we've got our alternate interior angles helping us give that two lines are parallel to each other, well, now we can keep going. So we can now state that FG is perpendicular to GH, and we know that because it was given to us. And then we can utilize the fact that we have these two lines are perpendicular and these two lines are parallel to finish it off. So we have EH is going to be perpendicular to GH, and the reason for that would be the theorem that we just finished proving, and it would be the perpendicular transversal theorem. So that's how you would use that theorem inside of another theorem. Otherwise, you would have had to go through and prove this whole theorem inside of this proof here. So theorems help shorten up your proofs a little bit. Well, that ends our lesson on perpendicular lines.